Hello, everyone. My name is Uri, and I work at Certora. And we're going to take a stroll together down the security tools zoo. And by security, I mean specifically security against smart contract bugs. So there are very many tools in existence that will help you find bugs in your code. And a lot of them use some somewhat obscure technologies with names like formal verification or static analysis, terms that not everybody has learned at in school. And it sometimes feels that in order just to catch up with all these new terms and technologies, you need to be an expert. So our goal today would be to demystify most of these terms and what do they mean. We're going to look at the different tools through a practical point of view. What are the advantages and disadvantages of each of them? Each of them will be compared to an animal because different tools are like different animals with different behaviors, need to be fed different food or different inputs, etc. We'll also look at how you can use these tools effectively to find bugs, and we'll see some cute animals along the way. The first building block for finding bugs in smart contracts are tests. And obviously, you must be familiar with it, but we'll have to cover it anyway, because that's a basic building block. So in this talk, we're going to look at a specific flavor of a transfer function that takes two different addresses, a sender and a recipient, and a certain amount of tokens that we wish to transfer. On the screen, you can see an example of a test in Solidity written for Forge. The test says that we're transferring one token from Alice to Bob. And after the transfer, we check that Bob's balance of that token is exactly 1. So what we can notice about this test is that we've checked a specific input, right? 1 token, that's the amount that we chose. But also 2 specific addresses, Alice and Bob. And we also checked a specific scenario. A scenario, as I define it here, is just a sequence of specific functions. So far, that's pretty trivial. But one thing people tend to miss about tests is that they always start from a specific starting state. In Forge, we have the setup function that you can see behind me that initializes the balances of Alice and Bob. And we're not going to check how the transfer function behaves for any other initial balances of these addresses. So some unit tests for the transfer functions, you might be familiar with it. You can try to send 0 tokens or the maximum amount of tokens or to the 0 address or to yourself, etc. Tests are very useful, but they're like a mole. They're blind. They can check only the very specific things you told them to check. They're still very useful in practice, and mostly because they're cheap, they're easy to write, and they're highly explainable. You wrote the test, you wrote it for a reason, you hopefully know what it is, or at least knew once, so you always have a starting trail to find out what's the problem if a test failed. And we'll see that's not necessarily always the case with other tools. So obviously, tests do not suffice. We want to increase our coverage for more inputs, for more starting states. If we want to do that, we can use a fuzzer. There are several fuzzers in the market. One of them is Echidna by Trail of Bits. Forge by Foundry has it. Harvey from Consensus Diligence, and there are many more. The idea of fuzzing is simple. We're automatically generating a large quantity of inputs and test them. Obviously, the more inputs we test, the higher our confidence is that the code behaves as expected. Obviously, one bad input is enough to find a bug. So on the screen, you can see some examples that a fuzzer might generate. So this begs the question, how do we generate those inputs? They could be generated randomly, But actually, most fuzzers don't do that. Most fuzzers are smart to some extent. That means that they either try to choose different inputs to cover more branches in your code, or try to copy values from the storage of the contract, and so on. So that's the difference between fuzzers. Their difference in intelligence in generating automatically those inputs. Some fuzzers are even smarter than that, and they can do something called invariant testing. Let's start by what is an invariant. An invariant is something about your code that is always true. It started true, and it will continue forever to be true. And one example is for a token. We say that the total supply of the token is equal to the sum of the balances for that token over all the different addresses. That's something that must always be true. So how do fuzzers check for it? They simply generate also a random sequence of functions, which are called one after the other, with some generated inputs. And then the invariant is tested after each function call. Okay, so we see that fuzzing is pretty strong. However, it's still not covering everything, right? There is a theorem called the infinite monkey theorem that says that if we give a monkey a typewriter and it's gonna hit random keys on it, the monkey will eventually write down the entire works of William Shakespeare. And fuzzers are similar to that in principle. It's kind of a brute force approach, could be more or less intelligent, but we're trying to find sometimes very rare and specific bugs. And at this task, fuzzers don't excel. So fuzzers are monkeys. They're cheap and easy to set up. In many testing suites, will allow you to extend them, to extend your regular tests to fuzz tests very easily. However, they don't cover everything. They leave some inputs or starting states to uncovered. And to give you more motivation about why we need this, this is an example from MakerDAO. MakerDAO have a stablecoin called the multi-collateral DAI. And there is an equation called the fundamental equation of DAI that tells us what is the relationship between the debt that the token took and the amount of tokens in existence. And it should always hold true, except that it didn't. And they found this a year ago, after the code has been deployed for a while. And I'm not going to get into the details about what could break it, but this is the minimal example that shows us what can break this invariant. And what's interesting is that we need to execute 8 different functions in a specific order with a specific relation between their inputs. So this is something that we could stumble upon if you fuzz long enough and hard enough, but it's very, very unlikely. So what can we do to find bugs like this? Turns out that we can do something, but that requires a shift in the way of how we think about the problem. If we remember something from high school, I think most of us have heard about the Pythagorean theorem. The Pythagorean theorem is a statement about triangles. And it was proven to us, but after it was proven, we don't need to check it on triangles, right? We didn't check all the triangles in existence to know whether this theorem is true or not. And this is exactly what the next type of security tools will try to do. We call it formal verification. The goal, the aim of formal verification tools is to transfer your code into math and then prove something about it using mathematical methods. It also requires that we make our tests math. We call those math tests specifications. So there are several types of formal verification. We're going to talk about only 2. We're going to talk about symbolic execution and about interactive theorem proving. Before we delve into what they are and what are their differences, let's look at an example of such a math test, again called specification. This one is written in the Certora verification language, which is the input language for Certora's formal verification tool called the Certora prover. If you look at it, it looks kind of similar to the test that we saw before. We're again checking the same transfer function. So we check the balance of Bob before the transfer. Then Alice transfers some amount of tokens to Bob. And now we assert that the balance of Bob grew exactly by that amount. It could be broken, for example, if a fee was taken out of this transfer. So what's different between this and the test? We didn't transfer 1 token or 5 tokens. We transferred an amount of tokens, which we did not specify. And that's because it could be anything. It's like an x in a mathematical equation. Interestingly, the same is also true for the addresses. They have not been initialized to have any balance. And these addresses could be the 0 address, could be the same address, could be the address of the token, and so on and so forth. So it's a generalized form of a test. Okay, the first type of formal verification tools are called symbolic execution tools. There are a few in the market. Again, there is the Certora prover, but there's also Manticore by Trail of Bits and Mithril by Consensus Diligence. And the way that symbolic execution works, we need to give the program 2 different inputs. We have to give them the contracts that we're trying to find bugs in and the specification that we saw earlier. And it will give us 1 out of 3 possible outcomes. 1, it says the test passed. We say this is a proof because it's true for all the different inputs and starting states. The other option, and probably the best option for us, is a violation. So something is not right, and then it will give us a specific scenario where the test fails. So a combination of a bad starting state and bad inputs that led to an unexpected result, which can very often be a bug, and maybe a rare to find bug. And the third option is that it can tell you, I don't know, and just time out. So symbolic execution tools are like turtles. They give us maximal protection because we cover everything, all the starting states, inputs, and scenarios. It can prove to us the absence of specific bugs, the bugs that we wrote in the specification, which is something that we couldn't do before because we're not using mathematical methods. And we see in Certora in practice that just the process of writing a specification for your system is enough by itself to already unravel some bugs in the design or the implementation. So just the process of writing the tests is also helpful. However, it's far from perfect. Like every turtle, symbolic execution is slow, and it takes hours to run. It's also bounded in practice. The problem is very resource intensive, and so we have to limit the program in some way. For example, we often limit the amount of loop iterations that we cover. We can't prove to you that the program will not have this bug if we allow the loop to run for 100 iterations. Even worse, the problem is what we call in computer science undecidable. It means that no matter how smart we make the formal verification tool and how much time and resources do we give it, it will always time out on some combinations of programs and specifications. So in practice, it means it can time out, and it does. Probably an even worse limitations in terms of practical use is that you have to write specifications for it, which take time to learn how to write them and takes time to write the correct ones. Because these tools, formal verification tools, are only as good as the specification that you give them. If you give them incomplete or incorrect specifications, they will not catch bugs in your code for you. The other type of formal verification tools are interactive theorem proving tools. The main one in the market is the KEEM framework by Runtime Verification. The big difference here is that we give it another input, a mathematical model of the virtual machine. So it has been created once by runtime, and it can be used again by all of their clients. So it's not another burden for you. However, it can give you two different outcomes. It can either prove to you that the bug is not present, which is great, which is what we had before, or it can go to an unknown state, meaning I cannot prove this. And very often, it's just something that doesn't stem mathematically from the inputs, meaning that the user has to provide hints. So this is why we call it interactive. It needs some human interaction to get to these proofs, to get advanced and finish running. So theorem proving is like an elephant. It can carry great weights. The K framework has been used to verify much more complex systems than smart contracts. It has been used in airplanes and submarines. It's also, as I said before, not bounded by the amount of loop iterations. It doesn't have any of these kinds of limitations. It can prove things in a higher, more mathematically abstract way. But in practice, they are hard to use because it takes a large amount of expertise to give the tool the correct hints for it to continue to run. And also, there is a problem that if the tool cannot prove something, we can't easily tell if that's because we didn't give it the correct hint or because the code has a problem. And we also don't know where the problem lies in the code. So it has low explainability. So writing specifications is painful, is difficult. Luckily, all these formal verification tools can do something without specifications. They can check for revert conditions in your smart contract code. It could be assertions in the code or division by zero and so on. All the tools support this, and now actually the Solidity compilers comes with the SMT checker out of the box that can also do this for you. However, that's obviously very, very limited in what it can do. So what else can we do without writing tests or specifications? We can use static analysis tools. And there are several in the market. There is Slither by Trail of Bits. There is ones by Veridice and Consensus and many more. Static analysis tools don't actually write your code, they just examine it. That's why they're called static. And they each have a list of detectors that are trying to find some predefined common bugs in your code. Behind me, there is a list of detectors from Veridice. We can see that they can look for re-entrancy bugs or reading from an uninitialized state variables, and so on. And the difference between the static analysis tools is going to be, among others, by the list of detectors. So static analysis tools are like a goldfish. So they're low maintenance and cheap, they're easy to write, they're usually just plug and play. They're also pretty like a goldfish. It will tell you exactly what the problem is. The detector will tell you, in this function, there could be a re-entrancy. However, a goldfish is confined to its aquarium. Static analysis tools are confined just to find the bugs or pre-programmed to. They're not going to find a specific logic bug for your system. They're just not built to do that. But actually, from a user point of view, the largest drawback is just that you have lots of warnings and errors. There are lots of fish in the sea. So behind me on the screen, you see the output that I got while running Slither, one of the static analysis tools, on one of the Solidity contracts we use for regression testing in Certora. So it's over one page long, and none of them are actually real bugs in the code. So a lot of the time that you save by not writing tests or specifications, you lose by engineer time that has to look through all the output and tell whether it's relevant or not. So before we move on to the next topic, just a remark. In practice, all the different tools employ some combination of technologies. They're all hybrid animals. At Certora, we use static analysis to improve formal verification. In Consensus, they use static analysis to improve fuzzing. In Veridice, they use fuzzing to improve static analysis, and so on. So we've covered quite a few different technologies, but how can we know that we use them effectively? We think that we have a mighty hippo that can trample all the bugs, and we actually have a baby. So there are several ways to do it. One of them is human inspection. We'll have an engineer read all our tests, or specifications, or static analysis output, and tell us if it makes sense, if it looks good, if we missed something. Another commonly referred to stat is the code coverage. It could be line coverage or brand coverage, and many fuzzers or testing suites can do this for you automatically. And there is another option, another way to do that, which is called mutation testing. The idea is that you take your code and include a random fault in it. The code with the random fault is called a mutant. We expect our testing suite to fail on the mutant, to locate and find, hey, there is a bug, something is not working correctly. Obviously, the more mutants we generate, the higher our confidence in the score that we get. So let's see an example. Behind me is a Solidity code for the transfer function, which contains no bugs. A mutant for it might just decide to comment out the first line of code. So obviously, that's a wrong implementation of the transfer function. And if none of our tests or formal verification or static analysis says to us, hey, something is wrong, that we know that we're not really covered that well. Certora has a free mutation testing tool for Solidity called Gambit. Okay, so what are the takeaways? We have looked at quite a few different technologies for smart contract security. Each of them is different and behaves like a different animal. Each has its advantages and disadvantages, and the food it requires, which are the inputs, and none of them make the other obsolete. Each of them has non-overlapping advantages and disadvantages. We say that in security there is no silver bullet, and that's still true. And to get the best security for our smart contracts, we should use a combination of different tools. Thank you. Are there any questions?
Hi. Thanks for that. That was great. The tools that you went through are all provided by, Certora, Consensus, etc. Sorry, echo. How does the market decide that those are the best tools for usage? Like, what are you seeing that directs you to Trail of Bits over Consensus, or and how do you incorporate that in the Certora products?
So the tools that I've talked about here are some of the more commonly used ones. There are many others. Some are open source, some are closed source. Each one of them has, there are more differences than one I've just told. Like in practice, like some of them support different ways of including tests, right? Different runtimes, better support from the team. So in a product point of view, there are more differences than just the technology. I'm not sure if it answered the question. Yeah? Oh, you can clarify, no?
Thanks for the nice talk. Can you give a short example of the K framework? It sounded really astonishing.
Say the last few words again.
The K framework sounds really astonishing for me, or I'm quite curious how it could look like.
What they look like?
Yeah, as an example, probably.
An example of how does their specification look like? I think some of it is available online. I don't have it here with me. Okay. Yeah, but they're verified a few projects. They've actually verified the EVM itself, which is a very large scope project. And they've been working with Maker, and they have other customers. I can help you find examples later.
Great talk. So we have definitely used fuzzing historically, Echidna mainly. and we have tried using Certora in the past. Will you say that if you allow your fuzzer to run for a given amount of time long enough, that the space of variable inputs are more or less covered? The reason I'm asking is we found it hard to learn a new language, and then another challenge is we have to put our code on your machines, which for a product which is, for example, confidential in nature, we would not like to, because all other tools, I can run Echidna, Slither on my machine. I don't have to, before releasing it to the public, put code outside the environment, and I work for a bank and we are conservative in that regard. So how will you solve that problem of exporting your code beforehand, because your problem space, and that's why we continue to use Echidna and not migrate it to Certora.
So we see in projects that very often fuzzing and formal verification and also static analysis don't find necessarily overlapping bugs, right? Sometimes fuzzing finds edge cases that you never wrote specifications for, and the opposite. We can see that in many projects, including, by the way, with the Solidity compiler, for example. From a security point of view, it's better to get yourself covered from all angles. Of course, in practice, you have a limited budget, and you need to think accordingly of what you can do. So about the problem of fearing about revealing your code before you formally verify it. So there are a few options. There are now a few free formal verification tools like the SMT checker, and yeah, I guess in any closed source product, you need to have some sort of trust about who you give your code to, right?
Is there a managed solution which is out there?
Not at the moment. We're thinking about it. Any other questions? Thank you.